We're continuing with the NCERT textbook exercises. Identify the reagents shown in bold in the following equations as nucleophiles or electrophiles. Nucleophiles, nucleus loving, and they are electron rich, whereas electrophiles are electron loving, and so they are electron deficient. So OH minus and Cn minus, both of these are nucleophiles, whereas CH3CO plus is an electrophile. Classify the following reactions in one of the reaction types studied in this unit. I know we've not studied the types of reaction in this unit, but so there are four basic types of reactions: addition, elimination, substitution, and rearrangement. So in addition reaction, you have a substituent getting added. In elimination, it's the opposite. Substitution reaction, a substituent is replaced, whereas rearrangement, there is, as the name suggests, rearrangement of the atoms. So in case of the first one, the Br is getting replaced with SH. So there is a replacement, which means this particular type of reaction is a substitution reaction. The next one here, HCl is getting added to this compound. Okay, and this is basically getting added, and this leads to the breakage of a double bond and became a single bond, right? So this reaction is an addition reaction. Atoms are getting added to the molecule. This next one is actually the opposite. The Br atom is getting removed, and that led to Br and a H over here. Both of them are getting removed. That led to a formation of a double bond. So substances are getting removed, which means it is an elimination reaction. So the first one is substitution because, as the name suggests, Br is getting replaced with SH. So it's getting substituted. Next, here a double bond is breaking and this HCl is getting added to the molecule. So it is an addition reaction. Whereas the third one is an elimination reaction because H and Br are getting eliminated. The last one, it's actually a little. First of all, this OH is getting replaced by the bromine atom. So here, if you notice, you have a Br, which means it's a substitution reaction. But the number of carbon atoms is seen to be different on either side in the first and the second case. So this particular reaction is both a substitution reaction as well as a rearrangement reaction. So the carbon chain, the chain length is the same, 3, 4, 5. Whereas this is 2, 3, 4, and 5. But the position of the substituent has changed. And not only, actually, it's not about the position of the substituent, but the carbon chain itself has been rearranged for us to get another molecule. This is a rearrangement reaction. So addition, you have substituents added. Elimination, you have substituents getting removed. And then substitution reaction, you have replacement taking place. And in case of the rearrangement, there is a change in the way the atoms are arranged. The next question. In this, what is the relationship between the members of the following pairs of structures? Are they structural or geometrical isomers or resonance contributors? So the first one, you have the CO group attached to the first, second, third carbon atom, whereas this is attached to the second carbon atom, which means they are actually structural isomers, positional isomers to be more specific, as well as metamers. Metamers because you have a CO group. Ketones can show metamerism, and the number of carbon atoms on either side is different. In this case, they have 2 carbon atoms. Here you have 3, and here you have 1, 2 each side and 3. So they are position isomers because the position of the substitute or the functional group is different in both cases. Here it is attached to the third carbon. Here it is attached to the second carbon. The reason I say the second carbon is to do with the nomenclature. Next is they're actually geometrical isomers. This is because if you notice the D and H. So you have 2 substituents, D and H, attached to each of these carbon atoms. When the same substituent is on the same side, it is called a cis isomer, whereas when it's on the opposite side, it's called a trans isomers. So these are geometrical isomers. The last one is actually a resonance contributor, because in this case, the movement of electrons is only taking place. Here, actually, the atom itself moved around. That's why we call them isomers. But in this case, the electrons are the ones moving, the atoms are in the same place. So these are resonance contributors. For the following bond cleavages, use curved arrow to show the electron flow and classify each as homolysis or heterolysis, and identify reactive intermediate produced as free radicals, carbocation and carbanion. So in the first case, you have a free radical being formed, and free radicals are formed by homolysis. So here you'll have a half-headed arrow. Here also you have a half-headed arrow. The next one, here you have carbonyl group, right? And basically, in case of a carbonyl group, it is supposed to be electron. The oxygen atom will tend to pull the electron to itself, right? So this in turn implies that the oxygen, the carbon attached to the oxygen will get a partial positive charge. So in case of this case, however, this carbon atom is attached to 3 other hydrogens. So this hydrogen is going to get attacked because this carbon has no hydrogens. OH will come attack this hydrogen, and then this this bond is going to get broken. Okay, positive for hydrogen, obviously, because negative. So this leads to the formation of a carbanion. It's a negatively charged carbon atom. So OH minus coming attacking the hydrogen. And because this is big, I mean, like as such, if you think about it, oxygen will pull the electron, this will get a partial positive charge. But in the presence of OH minus, this negative charge is going to come attack the hydrogen, one of the hydrogens of this carbon atom, and this bond is going to break through the process of heterolysis and lead to the formation of a carbanion. The next one here, this bond is going to break, right? So the bromine atom is more more electronegative, so it will pull the atoms towards itself, and it will leave the carbon with a positive charge and leads to the formation of a carbocation. The last one, this electron pair is going to come and attack the E plus, right? And so when this breaks, this is going to go to one of the carbon atoms, leads to the formation of a carbocation. So we discussed the arrow and like what it means. Half-headed arrow is always homolysis, and the double-headed arrow is basically the arrow itself is the heterolysis. Explain the terms inductive and electromeric effects. We learned about electromeric and inductive effects in the previous videos. So I'm just going to give a brief idea. Inductive effect is caused because of the presence of more electronegative atom in the chain, and it will lead to pulling the electrons towards itself, or pushing in terms of, if it's plus I or minus I, all of that happens. Electromeric effect, on the other hand, has to do with the substituent attack. If the substituent attacks carbon chain, and like the location on where it attacks and where it is joined in the compound itself is what is electromeric effect. If you really want a clearer explanation, I suggest you check out the video I did about inductive as well as electromeric effects. Which electron displacement effect explains the following correct orders of acidity of the carboxylic acids? The answer to this is inductive effect. So inductive effect, in case of Cl, the first one, it has 3 Cl3 groups, right? So the electrons are pulled by the Cl3, which makes it easy for the hydrogen atom to get removed. Okay, so generally COOH, the acidity or acidic condition of COOH is the fact that it can lose the hydrogen. So COO minus and H plus is formed. In case of a presence of 3 chlorine atoms, it makes sure that it's easier for it to lose the hydrogen. And even if it does, this gets stabilized by this negative charge on the oxygen will get stabilized by an electron withdrawing group. So that's why the acidity will decrease as the number of Cl groups are going to decrease. So it's a direct proportion. So Cl is going to act as a more electronegative group, and because of that, it is helping it basically. It's an electron withdrawing group, and so it's basically making sure the acidity of COH is high. So such effect is to do with minus I effect. Whereas in case of B, you have an alkyl group coming into question. So this is to do with the plus I effect. So the reason acidity is higher for a CH3 alone is because when this COO loses its hydrogen, then this is already electron releasing in nature, and when there is a negative charge, it will tend to destabilize it. And because of the plus I effect, so because of that, the acidity, on the other hand, decreases with increase in number of CH3 groups. I will do this question in the next video.